Welcome to the technical portion of the BP Learning Electronics Foundations Kit, Starter Kit. So today what we're going to go over are the basic electronics principles behind what we were doing in the Starter Kit. So if you watch the other video, I show you how to put together a breadboard that has a variety of components on them to light up lights and attach buttons. But I don't go much into the theory. We talk a little bit about how breadboards themselves work, but we don't talk much about electricity and how it works. So first, I'm going to start off by showing you kind of the first circuit that we did. So here is the first circuit that we looked at. And so the way this circuit works is you basically have your battery over here. You have the positive connected to the positive power rail. You have your negative or ground connected to the negative ground rail. Okay, and so the breadboard not only holds your components, it also makes connections. So on your positive, there is a wire that goes all the way across the breadboard here and powers this entire line. And on the negative side, there's a line that goes all the way across here. So all you have to do is hook up positive and negative power to that, and that activates that entire row. And so I can pull a wire off of any location on here and achieve my 9-volt battery. And likewise, I can take a wire to the blue line and achieve a 0-volt value or a ground value, and that will go to the negative terminal of the battery. Now these only activate one line at a time. Okay, so if we wanted to activate the other power rails, we'd have to take a wire from the positive power rail on that side to the positive power rail on this side, and then that would activate this whole side. And likewise for negative, we take a wire from the negative side over to negative. And it doesn't matter where you plug in your battery, as long as the positive is plugged in somewhere along this positive rail and the negative is plugged in somewhere along the negative rail, it'll supply power to the whole thing. So then we have our LED plugged in, and we have the long leg is on the more positive side. So we take the wire from the positive and bring it out to the breadboard. Okay, and so everything within these little rows, called terminal strips, have a wire on the back side connecting them. So because this is plugged into the same row as this leg, there's a wire behind it connecting them together. So the power comes out from the battery, goes through the positive wire, in to the LED on the positive side, comes out here, goes through the resistor, and connected in the same terminal strip as the resistor as this wire, comes back along the wire and out to the negative side. And this comes out through the negative terminal on the battery, and it completes the circuit. Okay, so that's how that works generally. So now it doesn't matter what color wires you use. It actually doesn't matter what color LEDs you use. They actually do make some difference, but all of our circuits will work no matter what color you choose. So any color you use here is fine, and any color you use for the wires are fine. But the first thing that we noticed about this circuit is that the 9-volt battery, is not a constant 9 volts. Now it'll work fine for this circuit because it's really a really simple circuit, but for some of our circuits we may want a more fixed voltage. A 9-volt battery, when it's heavily discharged, might be all the way down to 7 volts. Or if you get it brand new, it actually will be close to 10 volts. So especially if it's a rechargeable. So what we did instead is we added what's called a power module. And so this is our power module. And so you can see here, this is the same circuit, but instead of having our battery connected, we connected this power module. And this power module gives us a fixed 5 volts on each rail. Okay, and so we have to align the plus with the positive side and the negative with the minus side. But once you do that, it will supply and then you plug it into the jack to your 9-volt battery source, and it'll give you a constant 5 volts no matter what the charge of the battery is. So that'll give you a more fixed constant voltage. So, but the goal of this video isn't to talk about the breadboard itself, it's to talk about schematics and how we think about circuits. This is how we build circuits, but it's not necessarily how we think about them. So to look at the way that we think about circuits, I like to use a program called iCircuit. The nice thing about iCircuit is it's available for just about everything. It's available for Mac, for Windows. It's also available for the iPhone, for Android, and for, I think it's also on Windows Phone. And so iCircuit is just a simple way to play with circuits and to see what's happening without actually having to run a circuit. So you'll see that it has a list of sources that we can use. It has a list of analog components, a list of silicon components, a list of integrated circuits, and a few miscellaneous things. Plus we can add wires through here. So sources, what we have is a DC source. That power module can be represented like this. This is what a battery looks like in a schematic. You have the long line and the short line, and then it lists how many volts it has. And ours has 5 volts. So if we were going straight off of the 9-volt battery at relatively full charge, you could set this to be 9 volts. But in our case, we're using the power module, so we'll set it to 5 volts. Okay. And so coming out of our power, the long line is the positive side. We have an LED. Okay. This is the light. It's a light emitting diode. And so in the video we explained that a diode is a component that only allows current to flow one way. And so you can see the arrow points the way the current goes. And remember, when we're doing these things, when we're doing electronic circuits, we talk about how electricity flows from positive to negative. Even though the electrons themselves are going from negative to positive, we view this kind of like a vacuum cleaner, where we're actually looking at we're tracing the path of the suction that's pulling the electrons rather than tracing the actual path of the electrons. So that's why we always trace things from positive to negative. Okay, and so the electricity is going to go this way through the LED, the direction the triangle is pointing, but this line means that it's going to block it in the other direction. And then you have 2 little lines coming out, and that says that it's emitting light when electricity goes through it. So we're going to just stick this on here. And the nice thing about these electronic symbols, they're very simple to draw. So if all you have is a sheet of paper and a pen, you can draw yourself a circuit. It doesn't require any particular artistic skills. You just have to be able to draw lines. And so to connect these in a schematic, we'll simply draw a line from our battery to our LED. Now, what came after the LED? Well, we had a resistor. And put a resistor there. It doesn't really matter where on the screen you put these. Doesn't matter which way they're turned as long as the wires are drawn correctly. And so once we hook this up, we can see we completed a circuit, and now we can see electricity flowing and see that it now has a color on it because it is actively emitting light. Okay, so this is it's a 5-volt battery. And so what does it mean to be 5 volts? Well, in electronics, what we oftentimes do, electronics are, there's a lot of physics that kind of get in the way. But the goal of electronics is to kind of come up with a way of thinking about things where we don't have to worry too much about the bare physics involved. So we have kind of these idealized components that aren't quite, we have these ideal conceptions of components that aren't quite exactly what they are in real life, but they help us out a lot. So for example, this battery is what we call a voltage source. Okay? And so by voltage source, what that means is that under a variety of situations, under a variety of conditions, that is going to continue to produce 5 volts. Okay, so basically the way we think about it is that no matter what, this battery is going to produce 5 volts. It might change the amount of current running through it. There's several fundamental qualities. The two main ones are voltage and current. Voltage is how much push or pressure the electricity is exerting, and current is how much total electricity is moving. Okay, it's called. And then you have charge, which is the actual electricity itself. And so we can say that charge is the amount of electric stuff. All right, and then we can say that current is the movement of charge. Okay, and so we see these little dots going around, and that is the movement of charge along this path. Okay, so that's current. And then voltage is the amount of force, and actually it's potential force. So this has 5 volts. This component has 5 volts, no matter, even if nothing's connected, because that's how much potential force is between the positive and the negative. Okay, so this has a constant amount of potential force flowing through it, and then when we actually connect everything up, then that's the actual force. It moves from being a potential force to being an actual force. Okay, so now there's a relationship between voltage and current, and as I said, this is a voltage source. So that means that the amount, and as a source, that means it's always going to be that amount of volts. You can also have what's called a current source, although they're much more rare. A current source, and that would be something that gave us the same, that's weird, current source, and that would be something that gave us the same amount of current, no matter what same amount of current no matter what we were doing with it. So as a voltage source, this will always produce 5 volts. So then you might say, well, how much current is running through here? Well, there's an easy way to determine that, and that's using what's called Ohm's law. Okay, so let's write that up on screen. Ohm's law. Okay, so Ohm's law, it actually states that voltage equals current, that I stands for current, times resistance. So our current, right here, the I is measured in amps. You may have heard amps or milliamps. A milliamp is 1,000th of an amp. And the R is measured in ohms, and that's the measurement of resistance. So volts equals current times resistance. So for right now, let's pretend that this LED doesn't exist. We'll come back to it in a moment. So let's take this out of our circuit and just have our battery and our resistor. So volts equals current times resistance. Well, we know the resistance. It's 1K. A K is 1,000. So that's 1,000 ohms. So if we know the volts is 5 volts. That's how big our battery is. We know the resistance. That's what the resistor is. And so we can solve for what the current is. Okay. So come down here. If volts equals current times resistance, we know our volts is 5 volts. Our current is still unknown. And our resistance is 1,000. Okay. So using algebra, we can rearrange this. I equals 5 divided by 1,000, which means that I equals 0.025 0.05 amps, okay, which is the same as saying 1 milliamp is 1,000th of an amp. You can also say I equals 5 milliamps. It's spelled like that. Okay, and so this tells us if we just have the battery and the resistor, we will have 5 milliamps going through here. Okay, and so we can actually use this to find out how long the battery will last. Because the battery, typical battery is 600 milliamp hours. Okay, so that means we can run, so if we multiply milliamps times hours, it'll give us 600. So if we want to know how long the battery will live, we could just say 600 milliamp hours equals 5 milliamps times X hours. We can rearrange that and say X hours equals 600 divided by 5. And so our final result will be 120. So our circuit there can run for 120 hours. So not bad, not great, but not bad. And so this is kind of the thinking that goes into designing circuits. You say, well, how much resistance is there in the circuit? How much voltage is there? And so how much current is flowing? And so if you knew the current and the voltage, you could find out the resistance. Or if you knew the current and the resistance, you could find out the voltage, because this law pretty much stays the same. So then you say, well, what about the LED? What was that doing? Well, the LED, and now remember, all these things are, these are basically ideals. We're talking about an ideal scenario. Your battery is not exactly 5 volts. It's not 5 volts no matter what you do with it. We just think about it that way. And likewise, the LED has some characteristics that are idealized. They're not really that way, but we can think of them that way. So we'll drop the... Oh, I forgot to show you before we do that. So if you go in here, this will... iCircuit will tell you the voltage of everything and the current running through. So if I click on this wire, you can see up here that it is 5 milliamps at 5 volts. Now sometimes the negative and positive depends on which way the wire was drawn, so that's not so important, but it's 5 milliamps at 5 volts. And then down here you have 5 milliamps at 0 volts. So it drops 5 volts when it goes across that resistor. And if I click on the resistor, this VD stands for voltage drop. And so this uses up all 5 volts. And the reason for that is it's the only thing in the circuit using up voltage. The wires, again, under our idealized scenario, it doesn't matter how long they are. We just treat them as essentially direct connecting us. Wires do, in fact, have some resistance. They have other properties as well, but for short wires, it doesn't really matter. And for when we deal with idealizations like this, we basically ignore the properties of the wire except for the fact that it connects things together. So really the only part of the circuit that's doing anything is the resistor, and it's dropping 5 volts and has 5 milliamps running through it. Okay? So now what happens when we add our LED? When we add the LED, you'll notice that the current changes. We're now a smaller level of current. And the reason for that is that LEDs don't actually offer any, I'll say they don't offer any real resistance. They actually do offer kind of a resistance, but it doesn't play in much to our equations. The way to think about an about a diode in general is it's something that drops voltage but doesn't add to resistance. So in the case of this LED, a red LED drops 1.7 or 1.8 volts. Okay, so you don't deal with it in terms of resistance. So we have a 5-volt source, and so this LED is going to eat up basically 1.7 volts. So after 5 volts, we eat up 1.7 volts. So how many volts are left? Well, we can say 5 minus 1.7 equals, what does that equal? That equals 3.3. So there's 3.3 volts left after the LED for this resistor to eat up. And so if we use our same equation over here, V equals I times R, we can say, now we'll say 3.3 equals I times 1,000. I equals 3.3 divided by 1,000, and so basically our current will be about 3.3 milliamps. And if you click on here, that is about what it's running at, 3.27, which is close enough to 3.3. In electronics, there's always a little bit of fuzz because, as I said, these are not actually ideal components. iCircuit will model them more realistically than our equations will, but nonetheless, it's a workable assumption to say that a red LED will give us a 1.7 volt drop. Now, different colors will actually give us different voltage drops. So the red LED will give us 1.7 volts. A blue LED would give us about, I believe, 3.3 volt drop. And so each one will give us a different voltage drop. And so just to clarify terminology, when I say voltage drop, that's the difference in voltage between one side and the other. So this has 5 volts here, and on this side we're down to 3.27, and that's because of the voltage drop right here. And after the resistor, because each thing uses up a certain amount of voltage, after the resistor, we're down to 0 volts. Okay, we've basically used up all of our voltage when we hit the other side. The other thing that we did a second circuit with the same thing of LED and a resistor. Okay, and so we can model that here. Let's move it down a little bit. Give us a little bit more room. So we can add in a second LED and a second resistor. And this just hooks directly to power like the other one did. And this one, though, hooks directly to negative. It can't go in here because that's not where it connects in the circuit. It connects all the way around on the negative ground rail. And so here, on both these sides, we have basically 3.3 milliamps going on the other side of this LED. But on right here, right after the battery, we have 6.54, which is very close to 6.6 milliamps. And that's because charge is the actual stuff that's moving, and current is the movement of that charge. And so since we have 3.3 here, and we have 3.3 here, then if you add them together, the total amount of charge coming out of the battery is 6.6 milliamps. So that goes through here, goes through the circuit, joins back up, and you can see when it joins, we're back at our total value, and it goes back to the battery. Voltage, on the other hand, is we have all these areas are all at 5 volts. It's 5 volts when you come out of the battery, it's 5 volts here, and all of them, the thing about voltage is there's a law that says between any 2 points, the voltage drop will be the exact same no matter what path you take. So since this is a 5 volt battery, there is a 5 volt drop from the positive terminal to the negative terminal. And that's true no matter how we go about it. So if we go this way, there's going to be a 5 volt drop. If we go this way, there's going to be a 5 volt drop. If there was a more complicated way, it would still be a 5 volt drop. Okay? Now I want to show you what happens if you do something stupid, like directly connect the positive and negative. Okay? So let's say that we just have our circuit flowing here, but let's say that we stupidly connect our positive and negative power rail. Okay, so this gives us an error up here. It said wire loop with no resistance. Okay, and what that's saying is if you look at Ohm's law, voltage equals current times resistance, if we directly connect positive to negative, we haven't put any resistance in here, none whatsoever. So that means that if we calculate using Ohm's law, say voltage equals, what would say, 5 volts equals current times, what's the resistance? The resistance is 0. So if we rearrange this, we say I equals 5 divided by 0. What happens when you divide something by 0? You get infinity. Okay? So we wind up with infinite voltage. But it's not actually infinite because, again, these are idealizations. In actuality, the wire has some resistance, the battery has some resistance, and so the resistance isn't actually 0, but it might be very close to 0. So we get a very high current. And I think the batteries, they max out at about 1 amp. So your actual current is going to be about 1 amp of current. But that's still a lot of current, and you'll run out of that battery will be drained dry really quick. And so that's why we watch out for short circuits. We don't like them. We don't want them. We want to get rid of them as soon as possible. So anyway, so that's how it works. Oh, I forgot buttons. So now if we want to add a button into this, let's condense this a little bit, clean it up. So if we want to add a button in here, we can add a button. Now in this program, it's easier to manipulate switches and then turn them into buttons. So I'm going to make it a switch, drop it in, and then I'm going to set it to be a button. A button is also called a momentary switch. So here, notice there's a gap in the wire. So that's just the same as if we'd removed a piece of wire. So it can't, current can't flow because there's no wire. But if we push the button, then it closes the circuit and electricity can flow. Okay, see that? Now it really doesn't matter which side of the circuit we put this on. In fact, the resistor can go on either side either as well. In this particular circuit, there's nothing that needs to be on one side or the other. If we took this and put it at, that's not where I want it. If we put this somewhere else, put it down here, it would do the same job. See? It's just breaking it apart or putting it together. Either allowing current to flow or not allowing current to flow. And so we can do the same thing if we wanted to have another side of the circuit like we did in the other video. We added another LED. And this one also had a switch, or a button I should say. Had its own resistor. And it connected back over here. Change this to momentary, and so now I can turn on, oh, move this back to where it was. Okay, so now I can turn on either of these and get the current flowing independently. So just to repeat, this is a schematic, and each symbol has a special meaning and allows us to draw circuits just very simply and very easily. And so this is the symbol for a battery. This is for a button, which is also called a momentary switch. This is for an LED, and notice it's got the line showing that current can't flow the other way. So just to show you, if we were to put this in backwards, then even if we push the button, nothing would happen because it stops right at that line. That blocks it. So if we put it back in the right way, current can then flow. The resistor slows down electricity, basically. It resists the flow of electricity. And this has a 1 kilo ohm or 1,000 ohm resistance. And so that's the same thing we have over here. Now we can also adjust the resistor as well. We could say what happened if we had a 2K resistor. Well, it would basically be the same circuit, but the LED, it doesn't show it here, but the LED would not glow quite as brightly, and that's because the current would not be quite as fast. There'd actually be half as much current because we have twice as much resistance. So every time you double the resistance, you half the current. And so I don't remember what the exact level is when these things stop conducting. But 2,000 ohms gives you half the current. If we did change this to a 4K resistor, that gives you even half of that. We're down in the microamp level, the millionth of an amp. Let's see if there's a level where this will stop. Yeah, so now I see that it's not actually showing that our LED is emitting light because there's just not enough current flowing through it to do so. And in now all actuality, it'll probably emit some light, but you'd have to turn off the lights and look at it very carefully to see it. So anyway, so that is the main thing I want you to get from this is both that there's schematic drawings that they can tell us a lot about a circuit, and it's kind of independent of how you actually build it, right? Because in the circuit, we can build it like this. We can build it, we can put lots of different wires in there. This is the same basic circuit. It's just we added more wires just for fun. There's a lot of different ways to build it. You can even build it without any actual wires. Let's see if I have a... I don't think I pulled that one up. You can do it without wires just by directly connecting the LED to the positive onto the breadboard and the resistor going from the breadboard back to ground. There's a lot of different ways to wire it, and the schematic just gives us the way that we're thinking about it rather than the way that it's actually going to be wired on the breadboard. And then Ohm's law tells us the relationship between the main components of electricity. We have the voltage, which is the force, and that equals the current times the resistance. And the way to imagine that is if you imagine a garden hose. Now a lot of the analogies for electronics comes from water, where water is kind of like charge. And current is like the current coming out of a hose, or in a hose. And so if you imagine you're watering the lawn and the water is just kind of dripping out of the hose, but there's something way far away that you want to water, and you don't want to walk all the way over there. What do? Well, if you put your thumb over the hose, it causes it to squirt further. Okay? Now, a hose, rather than being a constant voltage source, is actually kind of a constant current source. So its current will always stay the same. And so what we're doing is we're increasing the resistance. So since voltage, which is the amount of pressure, equals current times resistance, as we push our finger on that hose, we're increasing the resistance. And since we have the same amount of current flowing, that'll increase the amount of push that's there on the coming out of the hose. So that's a way to think about it. But voltage equals current times resistance is what you'll need for pretty much any electronics project you want to do. So, and if this technical stuff isn't for you, our starter kits don't assume that you're going to know all this stuff. You can build the projects and learn about electronics components without having to do the math. But a lot of people do like to know the math behind it, and the math helps you to build your own projects and to understand, why did they use this resistor value and not that resistor value. And so the math helps you know that. It helps you know, well, what would happen if I swapped out a different component, all those sorts of things. And it'll also give you a good, if you know the math, it gives you a good intuition about what sorts of things do work and don't work. So I hope you join us next time for our next project kit. You can go to the bplearning.net website and learn all about our kits and learn where to buy them and what we have available. So hope to see you next time. Thank you very much.